here's another related rate example. In this case, in this problem, we have a rectangle, and basically the rectangle is changing shape. All right. So it says that at one point in time, the length of the rectangle is 20 inches, and it's decreasing at 1/2 of an inch per second. So in a second later, it'll be 19.5 inches. 2 seconds, it'll be 19 inches long. And at the same time, the width is 5 inches and increasing at a rate of 3/10 of an inch per second. So that, again, in a second later, it'll be 5.3 inches wide and so forth. And and what we're wondering is at what rate is the area changing, and then is the area getting bigger or is the area getting smaller? So we'll do this again this way. Well, let's start by looking at the relationship or at the equation, and of course that's area is equal to length times width. Now in this relationship we have three things that are changing, three variables. We have A, we have length, and we have width. And so let's list those variables and what we know about them. The length is equal to 20. The width is equal to 5, and the area, well, we know that that would be 100. We probably won't need the area. We may not need it. We'll just leave it up for emphasis. We'll leave it until we come back. And then we have the rate at which the length is changing. That would be dl dt. Okay, and dl dt is a negative 0.5 inches per second. Okay, the width is the rate at which the width is changing is dw dt, and that's 0.3 inches per second. Notice this is positive because the width is increasing. dl dt is negative because the length is decreasing. Okay, so now let's take a look at what we have. We'll take a derivative, just as we did before, a derivative with respect to t. Oh, by the way, I should have said this, dA dt, the rate at which the area is changing, is what we're looking for. Okay, so take a derivative of each side with respect to t. And on the left side, all right, the left side we have the instantaneous rate of change is dA dt. And on the right side, well, now, since L and W are both variables, they both depend on t, we'll have to use the product rule here. So we'll have the derivative of L with respect to t, all right, times W plus L times the derivative of W with respect to t. And this will give us a formula for dA dt, and now we just need to fill in the blanks. Let's see. And I'm going to use the units here just so that we can see we get realistic units. So dA dt is going to be dL dt, which is negative 0.5 inches per second, okay, times, all right, W, which is 5 inches, plus L, which is 20 inches, times dW dt, which is 0.3 inches per second. So let's see, multiplying these out, all right, negative 0.5 times 5 is negative 2.5, and I'll have inches times inches, inches squared per second, plus 0.3 times 20 is 6, all right, and so this will be 6 inches squared per second. And combining those, we would get 3.5 square inches per second. So the rate at change, the instantaneous rate at which the area is changing is dA dt, the instantaneous rate at which the area is changing, is 3.5 square inches per second. And then we're asked, is the area increasing or is the area decreasing? Well, since this instantaneous rate of change is positive, the area is increasing. Okay. All right, and this is another example of a related rate problem.